Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. In this lecture, I will move forward in taking the discussion of energy and potential, and today I will discuss another term which is called potential gradient. So in order to explain the concept of potential gradient, I will start from the basic mathematical expression of the potential difference. So potential is equal to minus line integral of E dot dl. So from this expression, we can write delta V is equal to minus E dot delta L, and this can be written as minus E delta L cos theta, and minus E cos theta can be written as delta V over delta L. So the maximum value of delta E over delta L is equal to minus E, and it will occur when theta is equal to 0 degrees. So this is the maximum value of delta V over delta L. And from here we can write E is equal to minus delta V over delta L max, right? So E is equal to minus delta V over delta L, and this thing will occur when we have theta is equal to 90 degrees. So when theta is equal to 90 degrees, it means the unit vector of the electric field is actually normal to the plane. So we will have a unit vector an over here, and this can be written as minus dv over d and an, and it means the meaning of this expression is that magnitude of E is equal to the maximum value of rate of change of potential with distance, right? So another thing in this expression is that the direction of E is opposite to the direction in which the potential is increasing the most rapidly. So the direction of E is opposite. So negative sign means the direction of E is opposite to the direction in which the potential is increasing the most rapidly. So this is the meaning of this mathematical expression, and dv over dl max is equal to dv over dn, and dv is actually equal to partial v over partial x dx plus partial v over partial y dy plus partial v over partial z dz. This is called chain rule, and dv is actually the total differential amount of potential, and in all the directions. So this can be written as the partial derivative of potential in the x-axis into dx plus partial derivative of potential with respect to y into dy plus partial derivative of the potential with respect to dz in the z uh, direction multiplied by dz. So this is our dv, and dv is also equal to minus e dot dl. So this can be written as minus ex dx minus ey dy minus ez dz. So we can compare this expression 1 and expression 2, and we will get, you can see that this here we have dx, here we have dx. So it means ex is equal to minus partial v over partial x, ey is equal to minus partial v over partial y, ez is equal to minus partial v over partial z. We can add all these three components to get total E, and total E will be equal to minus partial V over partial x ax plus partial V over partial y ay plus partial V over partial z az. Now this thing can be written as minus del V. So del is called a vector operator, and this vector operator is actually equal to partial over partial x ax plus partial over partial y ay plus partial over partial z az, and we can take this v as common and we can place this v over here. So this will become minus del into v. So del is a vector operator and it is a vector quantity, and v is a potential which is a scalar quantity. So if this vector operator is multiplied with any scalar quantity, it is called as gradient of that scalar quantity. So here we have minus del v, it means this is equal to minus gradient of v. So electric field can be defined as minus gradient of v, and in cylindrical coordinates, gradient of v can be written as partial v over partial rho a rho plus 1 over rho partial v over partial phi a phi plus partial v over partial z a z, and in spherical components, the gradient of v is also written over here. So whenever we have this vector operator with a scalar quantity, it is called gradient of that scalar quantity. If we have a dot product of this vector operator with a vector quantity, we will call it as divergence of that vector quantity. If we have a cross product of this vector operator with a vector quantity, then we will call it as curl of that vector quantity. So these are the three types of different operations which can be performed by using this vector operator. So now I will solve an example to elaborate more on the gradient or the vector operator with a scalar quantity. So we are given a potential field as 100 over z square plus 1 rho cos phi, and we are given a point. So first we have to evaluate potential at this point. So put these coordinates in this expression. So z is equal to 2, rho is equal to 3, and phi is equal to 60 degrees. So V at this point is equal to 30 volts. Now we have to calculate the electric field. Electric field is equal to minus del V, and this V is given in cylindrical component. So we will use this second expression. So partial V over partial rho A rho plus 1 over rho partial V over partial phi A phi plus partial V over partial Z A Z. So this is the partial derivative of potential with respect to rho. This is the partial derivative of potential with respect to phi, and this is partial derivative of potential with respect to Z. And after that we will substitute all the points, all the coordinates of this point 362 in this expression to get the electric field at that point. The magnitude of that electric field can also be evaluated by taking the squares of each component and adding them and then taking the square root. So magnitude of E is equal to 31.2 volts. Then we have to evaluate dV over dN. dV over dN is also equal to the magnitude of electric field, so it is also equal to 31.2 volts per meters. Now AN is the another quantity which has to be found out, and we know that electric field is equal to minus dV over dN AN. So AN is equal to minus E vector over dV over dN. So we are given this E vector, we also know dV over dN. So this unit vector AN can also be evaluated easily. In the F part, we have to calculate the volume charge density, and we know that D is equal to epsilon E. So we are given E, so we can evaluate D. So D is equal to epsilon E, and rho V is equal to del dot D. So after evaluating D, we have to take the divergence of this vector quantity D. So that will give us the volume charge density, and while evaluating the divergence of this vector quantity D, or epsilon times divergence of E, we will see that this term 1 over rho partial E rho over partial rho is equal to minus 1 over rho partial E phi over partial phi. So these terms will be equal, and when we add these first two terms in the divergence term, they will be cancelled out. So rho V will be equal to 1 over rho partial E rho over partial rho plus 1 over rho partial E phi over partial phi. Since they are equal and opposite, they will be cancelled out, and we will be left with only the final third derivative, which is partial Ez over partial Z. So this is the component of E along the Z direction. So this is easy. After evaluating its derivative with respect to Z, we will get some expression, and when we put these coordinates of this point 360 and 2, we will get this final answer, which is minus 234 picocoulomb per meter square. So I refrained myself from putting all the steps in this slide. So these simple steps can be evaluated by the students themselves. So that is all about our today's lecture on gradient of potential or potential gradient. I hope you have understood the concepts discussed in this lecture. For watching more videos, please subscribe this channel. Until the next lecture, it's goodbye.